That's how many tutors?
We've been in section 3.4. I have a couple of announcements before we continue on. One is the reminder that study group meets tonight. Now, study group was empty last week, and what the tutors do is if nobody shows up for 2 weeks in a row, they disband the study group. So if study group is something you might want to go to sometime, then go tonight, okay? Everybody who's interested in study group at all should go to study group on a regular basis, even if it's just for a few minutes. Now I know you're thinking, well, the quiz is a long way away. That's true, but some things need practice, and so the group leader will go over a few things with you to practice and prepare. And it won't take too long, and that way the study group will be there when you want to go. If you can't go to study group, you can go to the tutoring center and get tutoring, or you can have a Skype tutor. Any questions about the study group? Okay. A couple of students had submitted 3.3 answers instead of 3.2 answers. So if that was you in Canvas, I asked you to email me if you, well, no, I don't think I did. I'm asking you now. Please email me if you had just switched the two pictures around, okay? There were some people who didn't have the correct answer for 3.2. The question we asked in 3.2 is, how much bigger is the set of rational numbers than the set of natural numbers? So if you came to class or read your textbook, then you got that answer, and they were mostly correct answers. But I think that was a surprising answer, and that's why I had a number of answers that were incorrect. Okay, another announcement. Starting in section 4.1, which is Wednesday, and also on Friday, we'll need a few things for class, okay? So on Wednesday and Friday, bring a ruler, compass like this, okay, a drawing compass, not the north, south, east, west compass, and some graph paper. You don't have to go buy graph paper. You can print it out from templates online. You'll need about 10 sheets throughout the course of the semester, and you can just print those online if you'd like to. You'll also need the triangle templates, triangles. Here's my templates that are triangles. I'll show you where to get the templates for those. I have a couple different sizes. You just need the ones from Canvas. So let's go look there. It's triangles and one square. So on the Canvas homepage, you can collapse the class activities because those are kind of long. And then under the class activities are class activity materials. There you'll find the 4.1 Pythagorean triangle pattern. So these are just formed from 3x5 cards. You just take two 3x5 cards and cut them on the diagonal, and presto, you have the triangles you need. You also need one square. So that square is drawn to scale there on the page if you print this out. And you can cut that from a 3x5 card as well after you trace it. As you cut this square out, I'd like you to see if you can figure out how the length of the side is calculated, okay? The length of the side of the square does come from some of the lengths that you'll see in your triangles. So if you can figure that out, that would be a wonderful thing. Anybody have any questions? You just need one set of templates, by the way. Any homework questions? Okay. Well, where were we at? We were looking at questions in 3.4, these 4 questions. I'd asked you to decide which one was the most difficult to answer. Nicholas, would you please shut the door? Thank you. So the first question was, is there an infinity that is greater than the infinity of the set of natural numbers, thank you, and yet less than the larger infinity of the set of real numbers. Okay, so we found two sizes of infinity. The size of infinity that is the size the set of natural numbers are, the counting numbers, and the size of infinity, that's the size of the real numbers, all the numbers that you know that don't have an I. And the question is, well, is there a size of infinity in between that? Then the second question, is there an infinity greater than the infinity of the set of real numbers? Number 3, are there infinitely many different sizes of infinity? Okay, we have two sizes of infinity. Are there more? How many more? Number 4, is there a largest infinity, one that encompasses all others? So if you don't remember your choice, or if you want to pick again, you can pick out which one you think is the hardest question to answer. I forgot I can draw on here. Don't mean to do that. Let's see if I can clear that out. Okay. So let's go ahead and see if we can answer those questions today. So in 3.4, to answer those questions, we look at sets of sets. Now remember, we start small and understand something very thoroughly that's small, so we can use the idea on bigger sets. So we don't start right at different sizes of infinity. We're going to start with a set that just has 4 elements. We'll call the set S for suits, and then we'll list in there the suits of cards. So diamonds, hearts, clubs, and spades. So the cardinality of this set, or its size, is just 4. When we talk about cardinality, we're talking about the size of a set, but the word cardinality is used just for sets, whereas the word size has different connotations as well. So the cardinality of this set is just 4. Now we're going to make a set that is all the sets that we can make from the set. Okay, so we're making subsets. Subsets of S. So let's just first list the subsets of S, and by that we mean all the different arrangements we can make without respect to order of the elements of S. So we could make sets that just had one element, and we could make 4 sets that were subsets of S that just had one element. Looks like it froze up here. So we could make a set that just had a diamond, or a set that just had a heart, or a set that just had clubs.
I think it froze again.
It froze again. Why is it freezing again? Or a set that just had clubs, or a set that just had spades. So those would be all the sets we could make that just had one element, or we could make sets that had 2 elements from S. So we could make diamonds, and diamonds could go with hearts, so that would be a set with 2 elements. Or we could have diamonds with any of the other elements. We could have diamonds with clubs, or diamonds with spades. So we're making all the subsets that we can of the set S, and now we're on subsets with 2 elements. Well, that's the 2 element sets that have diamonds. How about the 2 element sets that have hearts? So we have hearts with diamonds already. How about hearts with clubs? Or hearts with spades? So we could have just used A, B, C, and D, but it's more fun to draw the hearts and such, right? All right. Let's see. So we have all the subsets that have 2 elements that have hearts. Now, what about the ones that have clubs? We have clubs with diamonds, clubs with spades, We don't want to miss any, so we want to be real careful. How about clubs? I said clubs with spades, but we don't have clubs with spades. Let's draw that. And now we have all the sets there are that we can make with 2 elements from the set S. Well, we could make sets that have 3 elements. So let's make all the sets that have 3 elements. We'll just leave off diamonds first of all. So that leaves hearts, clubs, and spades. And then we could make another set where we leave off hearts. So we'd have diamonds, clubs, and spades. Or we could leave off clubs. So that's diamonds, hearts, and spades. Or we could leave spades out. Then we'd have diamonds, hearts, and clubs. So we've made all the subsets of S that we can that have 1 element, 2 elements, or 3 elements. You can actually make a subset that's empty. So the empty set is a subset of all the other sets, even itself. Or you could make the subset that is all of the set S. So all 4 elements. So we're making all the subsets that we can of S, and what we're going to do then is make that a set, because today we're looking at sets of sets. So all we have to do to make all this collection into a set is put little commas between each set and put the set notation around it. So this is the set of all the subsets of S. So I'll write set of in front, and then we have set of subsets of S. We usually give that a name called the power set of S. So the power set of S is denoted with a large capital cursive P. We have the power set of S. The power set of S, all the subsets that we can make of S gathered together into a set of sets. That's the power set of S. So we are in search of larger sets, and we've certainly found a larger set than S now. We found a set that's all of the subsets of S, and it did turn out larger than S. Let's try it with a smaller set. Let's make the set called C for computers with Macs and PCs. So let's make the power set of the set C. So we're going to make all the set of sets that we can make out of the elements of C. So the power set of C. So we're going to have a set of sets. So we could have the set that has just 1 element, Mac. Or we could have the subset of C that has just the element PC. Or we could have the empty set. Or we could have the complete full set, Mac and PC. And that's all the subsets of the set C that I can make. So this time there was just 4 subsets. Still, that's larger than the set C was. The set C had a size of 2, and the power set of C had a cardinality of 4. Again, cardinality refers to size. Well, let's see if you're getting the hang of this. How about I give you an example of a set L for letters with the letters A, B, and C, capital A, capital B, capital C, and you go ahead and make the power set of L. Okay, so I'll give you a few minutes to do that. And I think I'll walk around and see how you're doing too. Maybe Nicholas will walk around too, and we'll see how you're doing. Raise your hand if you're stuck, okay? We're looking to make the power set of the letters here.
We're looking to make all the subsets you can of that.
If you're stuck, raise your hand, okay? So you can make all the sets that just had one letter, one element. So the set that has A, B, or C. Then you can make all the sets that have two elements. So you'd leave one out each time. And then you'd have the empty set. And then you'd have the set ABC itself. And I don't think I missed any. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Do you have 8? Okay, so there's 8 elements to the power set of the set L. All the sets that we can make out of A, B, and C, that makes 8 different sets. So it looks like we are finding a way to make sets that are larger than the size that we have started with. So these sets of sets come out larger. In fact, let's see how much larger they are. Okay, so we notice that the power set of a set S looks bigger than S. So we're looking for big sets, and it looks like we have a way to get there. Let's make a note of what we see. We see different size sets that we start with, and then we'll list the power set size that goes with that. So the smallest set we looked at had 2 elements, the set C, and in the power set we came up with 4 elements. We had a set L that had 3 elements, and that came up with 8 elements in the power set. And we started with a set that was larger, had 4 elements, and it had 16 elements in its power set. Did I miss any? Let me double check. 4, 10, okay, 16. Does anybody see a pattern here? Can anybody describe the pattern? What is the pattern? Yes?
You're doubling the power set size.
Good, it doubles. Yeah, so this was 2 times 2, and this was 2 times 2 times 2, 2 times 2 times 2, times 2. So we just keep doubling when we add an element. And that's because for every element you have the choice to be in your new set or not in your new set. So each element has 2 choices, and that means we get these doubling every time we add an element. So we started small with finite sets, and now we'll move this idea to a large set. We'll move to an infinite set. we're going to consider the power set of the natural numbers. Now, eventually, we're going to want to put these in a one-to-one correspondence. So as we look at what the power set of the natural numbers would have for elements, we're going to list them on the right side of the page here. Okay, so remember the natural numbers are just the counting numbers. 1, 2, 3, 4, etc. So we're making all the subsets that we can of those, or at least we'll get a representation and a feel for what those would look like. So all the subsets we can make of the natural numbers, and those, if we list all of them, would be the power set of n. So some elements might look like the set with the number 2 and 3. Or we saw the empty set, right? The empty set was a subset of all the sets. Or we could have an infinite subset of the natural numbers. We could have the numbers 2, 3, 4, ... go on forever. So there's an infinite set, that's a subset of the natural numbers. So that set would be in the power set of the natural numbers. We could have just a single number, like 100. Or maybe there's 3 numbers in our set, but some of the numbers are kind of big. So I'll have 5, 100,000, a million. I'm not going to put commas in my million and 100,000 though, because that will get really confusing when I'm trying to make a set and I'm separating them. Okay, so I have 5, 100,000, a million for one of my sets. How about a set with 5 elements? 1, 2, 3, 4, 5. Okay, so we could have any number of elements in a set. How about we do one with 7 elements? 7, 8, 9, 10, 11, 12, 13. I think that makes 7. Yeah. And I'll put ... okay, because I can't list an infinite number of elements. But let's just put one more. How about we put the set with multiples of 5s? 5, 10, 15, 20, 25. So another infinite set. So we have another ... going on to show this goes on forever. So all the subsets we could make of the natural numbers would go on forever, but we have a little bit of a representation here. Now when we looked at these finite sets, their cardinality, the cardinality of the finite set was smaller than the cardinality of the power set formed by them. We can find out if that's the case here as well. So now we're looking at an infinite set, and we want to find out, is its cardinality larger than the cardinality of n? So let's see if we had all of this infinite set listed, if we could put it into a one-to-one correspondence with the natural numbers. Okay, so we'll say this is fixed. Like there is a way to list, if there is a way to list all of the power set of the natural numbers, then it's listed, and it's a fixed list. And it's in one-to-one correspondence with the natural numbers if there is a possible way to do that. Let's see, we have a ... there, so I'll go ... And then, I don't know what number this is. Let's say it's 11. Okay, ... Okay, so if there is a way to list all the elements of the power set of n, then I'm going to fix this list and make a one-to-one correspondence with n itself. So we're looking for sizes of infinity. So we're going to see, is the power set of n, is the power set of n the same size infinity as n? Do they have the same cardinality? Are they in a one-to-one correspondence? The life lesson in this section is whenever we have an idea, we should push it as far as possible beyond its original context, beyond its original context. So what we're going to do is push the idea of Cantor's diagonalization proof beyond what we used it for before. So we're going to create M. Okay. We're going to create M, just like we did for when we tried to make a one-to-one correspondence between the natural numbers and the real numbers. We're going to create M, a missing set. And here's how we create M. We're going to include the natural number if it is not in the corresponding subset. So we're theorizing that we have, in fact, made a one-to-one correspondence between the elements in the power set of n and the natural number itself, the set of natural numbers themselves. And now we're testing that by seeing if it's possible to create M, a missing set. And here's the process we're going to use. So let's write M down. And M is a set, because the elements of the power set of the natural numbers are sets of numbers. And what are we going to put in M? Well, let's look. Okay, so first we look at the number 1. It goes with the set 2, 3. The number 1 is not in the set 2, 3, so 1 gets included. Then we move on to 2. 2 goes with the empty set, so 2 is not in this set. So we include 2. And then we go to the number 3. Here we come to a set where 3 is included. 3 is in this set that goes with 3, so we do not include 3. What we're doing is we're making sure M will not match any of these sets, because now it's not going to match the set that goes with 3 because it doesn't have a 3, and this set does have a 3. Now we go to 4. 4 isn't in the set that just has the number 100, so we list 4 in M. We come to 5. 5 is in this set, so we do not include 5 because we only include the natural number if it is not in the corresponding set. So by not including the 5, we're sure we're making a set that's not in the list over here. The number 6. 6 is not in that list, so we're going to include it. And now the set M will be different than the set that goes with the number 6. The number 7. 7 is in the list, so we don't include 7, because now we'll be different than the set that goes with the number 7. And then we'll put dot, dot, dot. And then we come to the set that goes with 11. 11 is not in this set, so we include the 11. Oops, that's not it, right? This actually is a set that's an infinite set, so I shouldn't close the set before I put the dot, dot, dot. So when you were looking for a missing set from the list, you can say, well, I can see that I could just have made a set with 1,000 and it would not have been in this list because there's no 1,000. But it might, the set with 1,000 would be on here somewhere. But now what we're doing is making a pattern that guarantees that the set M is not in this list, because we're different by at least one element from every set that's on the list. So we're different from the first element by including the 1. We're different from the second element set by including the 2. We're different from the third element set by not including the 3. And that's how this works. Include the natural number if it is not in the corresponding subset. So we're always different by one element. So M is not in the set. M is not in any proposed. M is not in any proposed listing of the power set of the natural numbers. So we found a set that is not in the list, and that means the power set cannot be in a one-to-one correspondence. The power set of the natural numbers cannot be in a one-to-one correspondence with the natural numbers. So the cardinality of the power set of the natural numbers is greater than the cardinality of the natural numbers. So we took a kind of long time to show this because what we could see easily with finite sets, okay, with finite sets we could easily see that the power set of the finite set had a larger cardinality. But would that be true with an infinite set? So we've shown now with the infinite set that the cardinality of the natural numbers power set is greater than the cardinality of the natural numbers themselves. This does in fact hold for all infinite sets, not just the natural numbers. We have Cantor's power set theorem. Cantor's power set theorem. For any set S, in parentheses, finite or infinite, for any set S, finite or infinite, the cardinality of the power set of S cardinality of the power set of S, maybe I should write it with words too, the power set of S is strictly greater than the cardinality of S. For any set S, finite or infinite, the cardinality of the power set of S is strictly greater than the cardinality of S. When we say strictly greater than, we mean greater than, not greater than or equal to. So the infinite we get from the power set of an infinite set is greater than the infinite size of this infinite set. So we found more sizes of infinity now, although we haven't. It turns out that the cardinality of the power set of the natural numbers is equal to the cardinality of the real numbers. So the set of all subsets of the natural numbers has the same cardinality as the real numbers. To prove that is beyond the scope of this class, though. If you're interested in different sizes of infinity and how do you show this cardinality and this cardinality are the same, set theory is a wonderful area to study. You don't need much math background and you can understand it. You just need a nice text that starts basic and works its way up. You can show interesting things like the set of all the numbers on the number line between 0 and 1 is the same size as all the points in the square on the Cartesian plane. So you can make a one-to-one correspondence between these points and these points. That theory is a lot of fun. Well, let's go back to our list of questions. I'll look at it in the book so I can point at things. Okay. Let's start at 2, because now we have a way to answer number 2. Is there an infinity greater than the infinity of the set of real numbers? And you will need to know these answers when you get to quiz 2. So I don't know if you want to write the questions down now or when we're doing the review. Is there an infinity greater than the infinity of the set of real numbers? Who can answer that now that we've looked at this? Let's look at Cantor's power set theorem again. For any set S, finite or infinite, the cardinality of the power set of S is strictly greater than the cardinality of S. So what does that say for question number 2? Is there an infinity greater than the infinity of the set of real numbers? You can nod your head or shake your head or go like this. What do you think? Would this Cantor's power set theorem apply to the real numbers as well?
Because we just said that quaternary is the same of real numbers at the bottom.
Oh, good point. Good point. So far, we haven't shown a cardinality greater than R, because we just showed that the cardinality of the power set of the natural numbers is equal to the cardinality of R. Okay, good. All right, so we'll ignore that then. You're covered up. Now just pay attention to, for any set S, finite or infinite, the cardinality of the power set of S is strictly greater than the cardinality of S. How does that fit with question number 2? Can we use that? What would happen if I put if I made the power set of the real numbers? What does Cantor's power set theorem say about the cardinality of the power set of the real numbers?
It will be bigger than the actual real numbers.
Good. The cardinality of the power set of the real numbers is strictly greater than the power set of the real numbers. So the answer to number 2 is yes. The cardinality, we'll abbreviate that, of the power set of the real numbers is strictly greater than the cardinality of the real numbers. Okay, great. Okay, so we're not going to try and show the power set of the real numbers, but you could, if you want to, experiment with what some elements of that would look like. How about question number 3? Are there infinitely many sizes of infinity? Well, we've found 3 sizes now of infinity. We have the size of the natural numbers, so that was the smallest infinity we found. And then we had the cardinality of the real numbers, which turned out to be the same size as the cardinality of the power set of the natural numbers. Okay. And then the cardinality of the power set of the real numbers is bigger than that by Cantor's diagonalization, by Cantor's, let me say this correctly, Cantor's power set theorem tells us that when we make a power set of a set, the cardinality is strictly greater. So the power set of the real numbers cardinality is strictly greater than the cardinality of the real numbers itself. So now we're up to 3 sizes of infinity. How much further can we go? Can anybody think of how you would make a set that has a larger cardinality than the power set of the real numbers? Good job, yes. The power set of the power set of the real numbers would have a greater cardinality yet. So the power set of the real numbers is a set. It's a set of sets. And you can make a set of sets, which is pretty cumbersome and hard to do. But you can do that. And again, by Cantor's power set theorem, that would be even bigger yet. And we can keep doing that. We can keep making power sets of power sets of power sets. And each time you'll get a larger set. So the answer, are there infinitely many different sizes of infinity, is yes. Because you can keep making power sets of power sets of power sets. Now this fourth question, is there a largest infinity, one that encompasses all others? The answer to that is no. Like, you can't make the biggest, humongous set that includes all the other sets because it can't have a power set itself then without being a set of its own subset. So it gives us what's called Russell's paradox. And you can read about that at the end of the section if you're interested. So number 2 and 3 is yes. Number 4 is no. So we have infinitely many sizes of infinity. The ones I think that are easiest to discuss we've talked about pretty thoroughly. Now what about this first question? Which one did you say was hardest to answer when you looked at these questions? Number 1, you were right. Number 1 is the hardest to answer. So this is the question. Is there an infinity between the 2 smaller infinities that we looked at? The infinity that's the size of the real numbers and the infinity that's the size of the natural numbers. Here's how your author states that one. Okay, so we have the infinite set of natural numbers. We have the infinite set of the power set of the natural numbers, which was the same size as the real numbers. Is there infinity in between? Bigger than the natural numbers, but smaller than the power set of the natural numbers. That is actually what the continuum hypothesis states. Does anybody know what is a hypothesis? What is a hypothesis? Yes?
An educated guess.
Yeah, an educated guess. And that this here we have the continuum hypothesis, which Cantor would have started with. There is no cardinality between the cardinality of the set of natural numbers and the cardinality of the set of real numbers. So that was an open question for decades as mathematicians tried to answer this question. So then, Kurt Gödel in 1940 proved that it is impossible to disprove the continuum hypothesis. Then, in 1963, Paul Cohen proved that it is impossible to prove the continuum hypothesis. So we have a very unusual and unique situation here. It's not possible to disprove the continuum hypothesis, and it's not possible to prove the continuum hypothesis. In other words, the continuum hypothesis can be neither proved nor disproved using the standard mathematical axioms and machinery. It's independent of our entire mathematical structure. Truly amazing and unique. So hopefully you've enjoyed looking at different sizes of infinity, and we're a little surprised by that idea, and maybe you can convince a friend that there's different sizes of infinity. I still have not convinced my husband, but on the other hand, he didn't sit through hours of lecture either, so I'll see you on Wednesday. We'll talk about this geometry then.
So then for number 1 is what?
Number 1 is impossible to prove or disprove.
Okay, let's go get you lunch.